All right, let's go ahead and get started. Any questions about anything we did last time before we get back into it? So I know it was we did some things that I think were difficult. So maybe if you had a chance to think about things or had a chance to take a look at some of the homework and have questions, did anything come up? Go ahead.
We have three functions.
Yeah.
It's like 2/x, and then you got two lines.
So if you're trying to, so I don't have a blank slide, but I'm going to draw this picture here. So what I think you're envisioning is something like this. You have function, function,
And another, like a line.
a straight line. Sure. Let's do the y equals x line.
So
Is this kind of what you're thinking about?
It's actually two lines and like a 1/x.
Yeah. So two lines in a curve, and I'm assuming you're being asked for an area like maybe from.
It doesn't give you an interval.
Oh, it doesn't give you an interval.
Yeah.
Oh, but it says to find the area bounded, so I'm assuming that would be this thing in here.
That's my question is like, which, if you have three lines, and let's just say the three intersects, or two of them intersect over on, over the right.
Sure.
Would you count that area as well? Like if they cross?
Yeah, so let me ask you this. So what I've shaded here, I'm making some assumptions based on the question you're talking about. But if it's the one I'm thinking about, you have an area bounded by not two functions, but three. So if I want to find that area, how many integrals would I have to set up? Three? What would those three integrals be?
You have a line.
The top, okay. So the top line's a function. The top line's a function, the curve is a function. So I have three functions, but that doesn't necessarily mean that I need three integrals. Because if we look at some of the other things we did last time, like this is one of the first ones we did, this might be the first one we did. You can do it with two integrals, but we got away with just one, right? So why can we get away with just one? So let's talk about the Riemann sum motivation for this kind of thing. So let's draw a rectangle in here. It's really about how to make these rectangles. So if I draw one here, what function defines the top boundary of that rectangle? Maybe I should give these things a name. We'll call this F. We'll call this G. We'll call this H. So for that rectangle I drew, what gives the upper boundary there? Should be G, right? What gives the lower boundary? So I think for one of these integrals, I can do the integral from 0 to whatever. Let's call this A of what integral? You said G minus F? G of X minus F of X dx. So I think that will give us that area for anything that's going on. Anything that's going on to the left of that crossing, because even though I only drew one rectangle, everything over here, we can still say that the upper boundary is G and the lower boundary is H. What about what happens to the right of A? We'll call this crossing point A. We'll call this crossing point B. So from A to B, what would this integral look like? So if I draw a rectangle in here, what gives the upper and lower boundaries for it? Shouldn't be G as the upper boundary anymore.
F and H.
Should be F of X minus H of X. Hold on, did you say G minus F for the first one? Should be H, right? So I think H is the lower boundary in both cases, but the fact that the upper boundary changes across that boundary means you have to, or across that X equals A vertical line. The fact that that happens means you need to set up a second integral. So yeah, there are three curves here, but at any given value of X, so for no matter what value of X I choose, how many curves do I have to worry about? Or how many functions do I have to worry about? 2, right? So you have to make a decision on what those 2 functions are, depending on what value of X you care about, which is why I have to set up these 2 different integrals. From the y-axis over to point A, I'm trying to find this area, which is between 2 straight lines. And from A over to B, the area I'm trying to find is between a curve and a straight line. So because of that, so we did one on Monday where we were able to get to an integral by changing variables. We were able to get to an integral where we could get by with only using 1 to find that area. I don't think that's true here. I don't think there's a way. In fact, let's actually demonstrate it. I don't think that, so I think if I draw a horizontal rectangle, like a dy rectangle here, what are the left and right boundaries for that rectangle? And what are the left and right boundaries for this rectangle? What is the right side of this rectangle? What function gives the right end of that rectangle? What gives the left? G. So that integral doing this in terms of y would be f of y minus g of y. What about this lower rectangle I drew? What gives the right boundary of this rectangle? And the left? G. So I think no matter which variable I decide to set that up on, I'm stuck with two integrals, which is common when you have more than 2 curves to worry about.
When you have that particular one, it doesn't matter whether you choose the Y or X.
Nope, you can do it both ways.
You would get the same.
Yeah. One thing I don't know if I've mentioned here, but if a function has an integral, it has only one integral. You can probably do it a lot of different ways, but the value is a unique thing. So it does not matter how you get there. If you do it correctly, you should get to the same, not should, you will get to the same value. You have a question over there?
Yeah, for example 3, why did we do f of y minus g of y?
That's a really good thing to revisit because that got really cloudy. We did a lot of stuff, but I think, hopefully I didn't just think about this after you were all gone, but I think we came up with like one kind of silver bullet reason why it made more sense to do this in terms of y than in terms of x. And to reiterate, you can do this in terms of x, it requires 2 integrals. So what was it that enabled us to do this with only 1 integral in terms of y? Fortunately, I won't be able to erase any of this stuff because we did it last time. But here's the kind of elementary rectangle I drew for dy. So same questions I just asked, what's the right boundary of that rectangle? The parabola, does it matter how high or low I draw that rectangle? Will the right boundary always be the parabola? Okay, what's the left boundary? Straight line, will that always be true? Okay, so sorry for how cluttered I think this is going to be, but what if I drew a vertical rectangle? What is the upper boundary for that rectangle? Straight line and lower boundary? Is that true for every place on that area I might do this? No, where would that fail? So once I cross this vertical line, then I'm comparing the parabola to itself, right? So if we decided to do this, to find this area in X, you need one integral for the left-hand side of where that behavior changes, and you need one on the right-hand side. So we can set up two integrals. If you can do one, you can do another one. So I think we might have said this very briefly, but this straight line, the way it's graphed is y a function of x on this straight line. What does it mean for y to be a function of x? What's the mathematical definition of a function?
Something in for x, you'll get one.
You'll get exactly one. Right. So if I put in one value of x, I'll get exactly one y value back, right? That's true for the straight line. Is that true for this parabola? No, this function, this parabola is not a function of x. So opposite question. Is x a function of y here? For this straight line, can I put in one value of y and always get one value of x back?
Yes.
That's true for a straight line.
Is it true for the parabola?
That's a good question. Is it true for the parabola? If I put in a single value of y, will I get one value of x? It's tricky. I think the answer is yes. One value of y is like a horizontal line, right? So let's go the other way. You answered very quickly and correctly no to the other question. Is this a function of x? No, because I could say x equals 2, and I get a point there, a y value there, and a y value there, right? But now let's say I choose y equals 1. How many x values does that give me?
Just one.
Just one, right? Is that true no matter where, how high or low I put my hand? So in the parabola, x is a function of y. And it's kind of weird to think that way because you don't usually think about functions in that direction. You think about x being the input and y being the output. But one thing we did with this equation last time, and I'll just rewrite here, is that this is equivalent to x equals 3 minus y squared. You agree with that? So now I'm saying that x is a function of y. Specifically, it's 3 minus y squared. If I take a number, any number you want, and square it, how many numbers will that give me? Not square root. Square root's a problem. Just one, right? You take any number, any real number, you square it, you get one result. Then if you subtract that number from 3, how many results do you get? Still one, right? There's nothing to give me like a duplicate when I use that function, that expression that I've written for x there. So in the parabola, y is a function of x, but x is not a function of, wait, did I say it wrong? X is a function of y, but y is not a function of x. Right? For every y value I give that function, I'll get a unique x value back. But I can give this thing lots of x values. For example, if x is 0, then what is y? Not for the line, the parabola. If I say x equals 0, what does y equal? Plus or minus radical 3. So I got many y values back. So I don't have the function relationship in that direction. So I think the rule of thumb we kind of landed on was this. If you can make basically if you can re-express whatever curve you're looking at or whatever graph you're looking at as a function in one variable, you should be able to get away with one integral. But yeah, I'm glad we revisited that. There was a lot that was going on with that example last time. Anything else? Okay, so we'll have more examples like that where it's sensible to change the boundaries, and we'll talk about why to do that and how. So let's do the examples on the slide. So I want to find this area. So while I'm erasing, take a look and tell me how you'd like to start. We can graph it. Do you remember what tangent looks like? I see some wild gesturing. So yeah, there are a kind of swirly pattern. Where do the asymptotes happen with pi over 2, and then every how often after that? Should be every pi after that point, right? So asymptotes at pi over 2, negative pi over 2. Let's just do one kind of curve in here too. Maybe that's all we need. If we need more, I'll draw more. But tangent sort of looks like this. Let's do better. So that's what the tangent looks like. Where's y equals -1? What other information do I have? X equals pi over 4. So not a great graph, but hopefully good enough to organize the things we want to do. Okay, so got a graph. How does that help? We can, but why? Right. So yeah, so I think the right bound is given to us. We're going to set up an integral whose upper bound is pi over 4. I don't know. I don't have a good idea as what the lower bound will be yet. So I think setting these equations equal to each other is a good move. What is the inverse tangent of -1? Should be negative pi over 4. So that should tell us our other bound, right? So I know I want to set up an integral like this from negative pi over 4 to positive pi over 4 of what? Awesome. I don't even know how to fix this issue. All I did was write down an integral of, no, I did more than that. Yeah, it's basically, we know what the right end of the area is because that's given to us with the x equals pi over 4. We don't know yet. Yeah, we didn't know what the left-hand side of that was. So yeah, now we got the bounds of the interval are negative pi over 4 to pi over 4. Come on. Okay. So let's do this combination low tech and high tech. I hate everyone. All right. So now you're caught up to me somehow. So how do we finish setting up this integral? We got the bounds from negative pi over 4 to pi over 4.
So we, to the integral as the tangent function.
You have to do like, would we have to do the bounds in y actually?
Why would we have to do the bounds and why?
Because technically you have a bottom function that is y equals negative. Below tangent of x past -1.
Okay, so that's a good point. So let me write down kind of the form of,
Or I guess, yes, tan of x minus -1. in my- 'cause-
but I'm glad this came up because I want to point out something that it might be getting lost here.
Yeah.
I believe this is the thing we've kind of been following, right? You take the greater curve minus the lower curve, integrate that over whatever your boundary is, right? What are f of x and g of x?
That's-
Oh, sorry, in general. They're functions, but like what specifically about the functions? When I say f of x,
y.
that's a y value, right? So even though it might look weird, this is totally true. Basically, I'm integrating from a to b of y2 minus y1 dx. So the thing that I'm integrating is a difference of y values. We're so used to function notation, we don't really think about it that way, but when we integrate, that really is what a Riemann sum is it's a bunch of rectangles. What does dx represent in a Riemann sum? Or at least with those rectangles? Yeah, what's that? Delta x, basically the change in horizontal width or the base length. So it makes sense that the other part of this is some kind of a vertical measurement. So some kind of a y height. So really your integrand that you're integrating is, it almost always looks like some function of x, but they really are y values. So in this case, to answer a very long way around your question is we can do this in one, I think we can do this with one integral no matter what direction we do it in. Probably feels more comfortable to do it in terms of x, so we'll keep with that. What is the greater curve in this case? Tangent of x, and what's the lesser? Right. Minus -1 dx. So simplifying, I get tangent of x plus 1. Is the integral of tangent something we know? What's that? Negative natural log of cosine? Where'd that come from?
Sine of x over cosine of x
Right.
equals cosine of x.
So that is something we've done a few times. That come if you basically we could set it up using u substitution, right tangent in terms of sines and cosines, but this does come out to be negative natural log of the absolute value of cosine of x plus x, right? How are we doing so far? Go ahead. Absolutely. So I'll put the question back to y'all. Where did the upper bound of pi over 4 come from? Right, so that one was given. I know what the right end of this base. I didn't know it was the right end of the boundary. That really, okay, so let's back up. I don't think this information was enough to tell us it was the upper bound. I think that information with the graph was enough. I think x equals pi over 4, that might be like, okay, that's probably a boundary of this. I don't know where the other side of it is. Let's draw a picture. Where did the other bound come from? So where did negative pi over 4 come from? Not for the x value. So basically, I know that y, so I have two functions going on here. One of them is kind of a trivial function, but one of them is y equals tangent of x. The other one is y equals -1. So for the same reason that, actually, let's just stay here with it. For a lot of the other examples we've done, we've found those intersection points, especially when I want to find the area enclosed or bounded by two different functions. I really need to know where they meet, where they cross. So that's why we set those two equal to each other. So that's where the negative pi over 4 came from. Good question. What else? Is this in, yeah, so now we can evaluate, right? What is the cosine of pi over 4? Root 2 over 2 plus pi over 4 minus the negative natural, still natural log of pi, radical 2 over 2, right? And that should be everything. So what do I really get then? Pi over 2. The natural log terms cancel, and I get pi over 4 plus pi over 4. How we doing? All right, any questions before we go do another one? All right, so let's just look purely at a graph this time. I do not have algebraic definitions for these functions, but let's put a context into this. So I have the velocities of two cars. Call the blue one F, red one G, and I'm graphing from 0 to 10. If I were to find the area between these two things, which we can't find exactly because I didn't give you any algebraic definitions, what is that area right there going to give you? Go ahead.
Would it be the distance between the two cars?
When? So I've drawn out that whole area. So I think you're right. I just want to make sure, I just want to be as specific as possible. So the distance between them, how long after they started driving? 10 seconds. Okay, that's, I think you probably meant that. I just wanted to make sure that, yeah, it's after 10 seconds, not like, it's not going to be like this variable thing. It's going to be whatever the distance is between them, right? So let's talk about a couple of things there. Let's talk about the idea of distance. Why is this integral going to give you anything having to do with distance?
The integral gives you the net change in over a period of time.
Gives you net change, but so what do the functions represent?
The velocity.
Their velocity, right? And velocity is a rate of change of distance or displacement. If they're traveling in the same direction and they're starting in the same place, then displacement and distance are going to be the same thing. But yes, the area between those two curves is going to be how much further the blue car is or has traveled than the red car. So if we wanted to, we could find, you could use some of our trapezoid Simpsons, any of our approximate integration methods to find that area. But I really wanted to talk about that interpretation. Are we okay with why that area is a difference in distance? All right. All right, I want to find the area bounded by these two curves. Thoughts on how to get started? Graph sounds good. What does this graph look like? Squiggly lines. I need more details than that, but squiggly lines, yes. I know what cosine of x looks like. So from 0 to pi over 2, Cosine starts at its maximum. When does it get to its minimum? Or when does it get to 0? At pi over 2? So this cosine graph should be like that, I believe. What does sine of 2x look like? Is the 2 amplitude? Ooh, no. What does it do? It shortens the wavelength. So basically, you're multiplying the 2 by the angle, by the variable, which means it's going to have the same behavior as a sine wave always does. It's going to run through those behaviors in half as much time, half as much change in x. So what does a sine wave usually do? Starts at 0. And it reaches 1 at pi over 2 typically, right? Which means for this one, it's going to reach 1 in half that. So it's going to go up to pi over 4. Does that make you mad? And then it's going to drop like this. So what's the area I'm actually looking for? It's bounded by what? 0 to pi over 2, right? So that's like the vertical, like that's like the horizontal interval. So I'm not going to look to the left of the y-axis. I'm not going to look to the right of pi over 2. So now I believe the graph is relatively accurate, at least good enough for us to organize what we're going to do. Can we start setting up an integral to find this area? What's it going to look like? There has to be 2 integrals, because what's happening here cannot be described by the same integral as what happens over here. So yeah, we're going to have 2 integrals. One that goes from 0 to some other place of what? So what's the integral that, what's the left-hand side of this integral going to look like? I mean, sorry, what's the function we're going to integrate?
So it would be the cosine function first.
Cosine x minus sine of 2x dx. And the other integral is going to look like what? The integral from some other place to pi over 2 of sine of 2x minus cosine of x. How can we find what the missing bound? We've got to set them equal to each other. So sine of 2x equals cosine of x. Here's a trig function that, or a trig identity that you might not remember. Sine of 2x is equal to 2 sine of x. Cosine of x. Where do we go from there? It's tempting, but I don't want to do that. Why can't I divide by cosine of x? Is it possible for cosine of x to be 0? It is possible. So I don't want to divide by it because that could cause problems. So let's do this instead. Let's do something that's sort of like division, but not as destructive. Let's factor out a cosine. So like cosine of x times 2 sine of x minus 1 equals 0. Where does cosine of x equal 0? Pi over 2. So there is a crossing point at pi over 2, but I already know about that one. Where does 2 sine of x minus 1 equal 0? So wherever sine of x equals 1/2, which is pi over 6. So there's our missing bound. So any questions on how we found the missing bound from our two integrals? Or why they have to be the same thing? If not, how do we continue from here? Integrate. What is the integral of cosine x? Sine of x. What is the integral of sine 2x? Or negative sine 2x? I think it should actually be plus, I think. So sine of pi over 6 plus 1/2 cosine pi over 3 minus sine of 0 plus 1/2 cosine of 0. What does that all come out to be? Uh, 1/2 plus cosine pi over 3 is 1/2, so plus 1/4. Sine of 0 is 0. So I think I get, yeah, sine of pi over 6 is 1/2. Cosine of pi over 3 is 1/2, so that becomes 1/4. And then 1/2, cosine of 0 is 1, so I get another 1/2. And then really we have the same antiderivatives to think about. So this should become the exact opposite of what we just had. Negative 1/2 cosine 2x minus sine of x. So negative 1/2 cosine of pi minus sine of pi over 2. Okay, maybe I should stop here for a second. How are we doing with where we are? What's the cosine of pi? 1, so negative 1/2. Wait, cosine of pi? Negative 1, so that becomes positive 1/2. Minus sine of pi over 2, which is 1, minus 1. Plus another 1/4. Minus the sine of pi over 6, so minus 1/2. So if I start adding all these things together, what do I get? Cancellation here. So on this side, I get minus 3/4, or let's just add them all together. I get 3/4 plus. The last half,
On the left of the column, you have the 1/2 plus 1/3 this one. Wouldn't that be negative because you're subtracting 1/0?
yeah, thank you. Okay, good. I was trying to figure out why that was coming out to be 0, and it should not be 0. You can see area. So that means I get 1/4. Why did the right one come out to be negative?
As the negative sine pi over 6, should that also be positive?
Yeah, for the same reason. But that's still going to make my integral on the right negative, which doesn't make any sense.
Well, then you have the 1/2. Right.
Oh, thank you. Thank you for saving me from myself. So what's my final result then? Looks like just positive 1/2. Yeah, I go 1/4 for each of one of those areas is a quarter. All right, so hopefully we're all repaired now. Any questions? Go ahead.
Like compared to the graph with that 1/2 represents.
It's a good question. So yeah, so now that we have a final number of 1/2, what does that 1/2 have to do with this picture? The area of which shaded region? All of them combined, right? So I think it's very much a coincidence that, so what's this area here on the left? We got 1/4, right? So it's kind of a coincidence they ended up being exactly, like they had to have to be identical on both sides of that line, but yeah, this area here is a quarter. This area here is a quarter. So that 1/2 we found is that total shaded area. Good question. What else? Okay, moving on. Let's come back to this one. I'm gonna do this one first. All right, thoughts? How do you know you're gonna have to do horizontal rectangles? Right, so there are parts, so there are, if I want to do vertical rectangles, by the way, I said have to do horizontal rectangles. That's not the issue. It's really, you could do it either way. It's just which one's going to be a little more direct. But if I draw a vertical rectangle there, let me ask it this way. I'm going to have to do more than one integral if I use vertical rectangles. How many integrals would I have to do? 3 integrals, right? So one where I'm comparing the blue parabola to itself, one where I'm comparing the pink parabola to the blue one, and a third one where I'm comparing the pink parabola to itself. We could do it. I think there are better choices to make. But what if I make a horizontal rectangle? What gives us the right-hand value or the right-hand boundary of that rectangle? So the pink, yeah, the pink one. Is that true no matter where vertically I am? In this case, that'll be true no matter how high or low, no matter how high or low I place that. So because of that, so let's go with the dy integral. How can we set that up? The integral from 0 to -3. How'd you get that?
Well, the balance. So we have origin is where they meet and
Okay, so this point right here that we're not labeling, let's label it now as 0, 0. Why'd you change from +3 to, or,
need the y value.
right? So one thing I want to make clear here is the integral we're going to set up is an integral. We're setting up a dy integral, right? Which means my bounds on the integral need to be x values. So basically we're setting up rectangles in the opposite way that we're used to. They're going to have dy thicknesses like this. But basically what I'm going to be integrating on is x values. So now what are those x values?
function equal 2y minus y squared.
I'm gonna, when you say top function, what do you mean?
Like, you know, if it's the y function of x, we would do top minus bottom.
Right. So it's all about which one's greater, right? And when you're talking about y values, then upper, higher is greater, right? But now we're comparing x values. Where are the bigger x values? On the right. So now I'm going to do my right function minus my left function. What is my right function?
2y.
Do we have to rewrite it, or is 2y minus y squared okay? We're doing this whole integral in terms of y, so I want to define my functions in terms of y. Minus what? Y squared minus 4y dy. So I believe that's a good setup for this integral. Questions? All right, what now? We can do some simplifying. And what do I get? 6y minus 2y squared. All right, what's the antiderivative of these things? Three y squared minus 2/3 y cubed. Plug in some values. So I get 3 times 9 minus 2/3 of 27 minus 0. So 27 minus 18 minus 0 equals area of exactly 9. How we doing? We feeling a little bit better about this than yesterday, or yesterday, Monday? So yeah, the area thing, yeah, when you start bringing in multiple curves, it gets a little hairy. I want to go back to this last example. We don't have time to do the whole thing, but I want to talk about strategy. If I wanted to find the area enclosed by these two things, how do we go about that?
What is that? Function y, so the function of x.
Which one are you talking about?
Well, both of them.
Okay. So you're talking about figuring out which is a function of which? Maybe I didn't understand your suggestion. Okay. So this y equals x minus 1 is y a function of x. If I take a value of x, any value of x, and subtract 1 from it, is there a possibility I get more than one answer? No. So I think that's a function of x. I could also rearrange it and get it to be a function of y. So I think straight lines in most cases are functions of x and functions of y. What about this thing here? Is y a function of x in this right-hand equation? Pick your favorite value for x. How many values of y do you get? You might get 2, right? So this thing is not, for this one on the right, y is not a function of x. Because of that, what kind of integral should I set up? In terms of y, this is going to be a dy integral. So that's as much as I wanted to say about it, because I know that was a big thing we talked about last time, which was how do we know when to make that change from the familiar integrals in terms of x to integrals in terms of y. So I think something to check is make sure the functions you're looking at are functions the way you think they should be. But real quickly before I say goodbye is this. If I were to rewrite this as x equals 1/2 y squared minus 6, that might be a little more convincing. This truly is a case where x is a function of y. No matter what I plug in for y, I'm going to get 1x back. as opposed to this. If I take a square root, what do I get? Y equals plus or minus the square root of 2x plus 6. That plus or minus means you're getting two values a lot of the time. How are we doing? Excellent. I will see you all either in my office hours or Friday. Take care.